Hello everyone and welcome. In today's video, we are going to take a look at the Fundamental Theorem of Calculus, Part 1. So in the previous video, we learned about the Fundamental Theorem of Calculus, Part 2. It's also called the evaluation part because it helps us evaluate definite integrals more efficiently using antiderivatives. So in this video, we're going to take a look at the first part of the Fundamental Theorem of Calculus, which is related to signed area functions and integral functions, and how to differentiate such functions. And to that end, let's begin by understanding what is a signed area function. So a signed area function of some particular function lowercase f with lower limit a is the following integral function. So let's call this signed area function a of x. So the variable of this function is x, and it's defined as the definite integral from this fixed lower bound a to this variable upper bound x that you're allowed to change, and then the integral of f of t dt. And so this is the signed area from a to x, right? That's one interpretation of the definite integral. And so I like to think of these signed area functions as like the area so far, and the function outputs the value of that definite integral for various values of x. So something I want to bring to your attention is that the variable of integration is t, and this will usually be like a dummy variable. You can use t, you can use u, but make sure it's different from the variable of the function. So in this case, the function's variable is x, and that is why x is over here, because that's what it varies. So when you change like 5 or 10, you're allowed to change the upper limit of this integral. The function inside will stay completely fixed, and then you can evaluate this integral using like techniques from the previous video. You can use the Fundamental Theorem of Calculus Part 2, or maybe some numerical methods if it's not possible to evaluate the integral. But yeah, the signed area function simply outputs the signed area from a to x of whatever this function is. So now that we understand what is a signed area function, we are going to motivate the statement of the Fundamental Theorem of Calculus Part 1 with an example before we look at the more general statement. So let's take f of x to be 4 minus x squared, and let's take our lower limit to be 1. So we're going to be finding the area so far starting from 1. Then we can define the signed area function a of x as the definite integral from 1 to x of, notice this is my f of t dt. So I'm using a different variable other than x here, 4 minus t squared dt. And so this signed area function represents the area from 1 to x. As you can see in this diagram, you can find the area from 1 to x. As you change this upper limit x, the signed area will change, and the function outputs that signed area for a particular value of x. Now, we can use the Fundamental Theorem of Calculus Part 2 to help us evaluate this definite integral, because that's what it is, right? This is just a definite integral where the upper bound just happens to be a variable. Usually we have numbers there, but you can treat it as a fixed constant for a second and use the Fundamental Theorem of Calculus Part 2 to evaluate it. So let's do that. To evaluate this definite integral, we are going to use the power rule on each of these two terms. So this constant becomes a linear, 4t, and then this t squared will become a t cubed, and then you divide by 3. And then you need to evaluate on the upper and lower limits. So you evaluate at the upper limit first, subtract the antiderivative, evaluate at the lower limit, which is this one, f of 1. Now we just go ahead and simplify these numbers, and you get down to this cubic function. And so this cubic function is the closed form solution to this integral function. Meaning that if I want to find the integral or the signed area from, let's say, 1 to 10, for example, then instead of having to recompute all of this work using the Fundamental Theorem of Calculus, since we did it in general for an arbitrary x, we can actually just compute a of 10 using this cubic definition. That's the power of this function over here. Now, what I want to bring to your attention here is the derivative of this signed area function, right? So we computed the signed area function, the closed form solution of it. Now let's try to differentiate this one. Okay, so a prime of x is just going to be the derivative of the result that just got over here. Now the derivative of 4x is just 4. And then the derivative of this one, you bring the 3 down, it cancels with this, and it becomes just an x squared. And then the derivative of a constant is just 0. So you just get 4 minus x squared. Now, does that remind you of anything? Well, it should, because this is exactly the function that we began with. It's exactly f of x. So what we see here is that when you differentiate the signed area function, you get back to the original function. So in other words, the signed area function is an antiderivative of the original function, because when you differentiate the signed area function, you get f. That's what it means to be an antiderivative. And now you might be wondering, was this just a coincidence? Like, did you make this example so that this happened? Or does this always happen? It turns out that the signed area function will always be an antiderivative of the original function. And so that brings us to the general statement of the Fundamental Theorem of Calculus, part 1. So let's suppose that you have a continuous function, lowercase f, on an open interval, and let a be a point in that interval. Then let's define the signed area function, let's call it a of x, as the integral from that fixed lower limit to that variable upper limit x of f of t dt. Right, so this is the area so far from a to x, the signed area so far. And so this theorem is asserting that the signed area function, defined in this manner, will always be an antiderivative of the original function on this interval. That is, when you differentiate the area function, the signed area function, you just get back the original integrand that you began with. Another way of putting this in more mathematical notation, when you differentiate an integral function, the derivative and the integral sort of cancel out, and what you get is the integrand evaluated at the upper limit. Okay, so you just get back the original function that you began with, f of x. And so here's like the summary. For continuous functions f, if you start with the function and you integrate to make the signed area function, and then you go ahead and differentiate that signed area function, you just get back to the original function that you began with. So these operations cancel out. So the fundamental theorem of calculus is basically asserting that every continuous function is guaranteed to have an antiderivative. And it also gives us a way on how to get that antiderivative. Usually these existence theorems in mathematics, they guarantee the existence of something, but then don't really tell us how to get that particular object. But what's special about the fundamental theorem of calculus is not only does it guarantee that every single continuous function has an antiderivative, but it also shows you how you can quickly write one down if you needed to. And that is just by writing down the signed area function. It's always guaranteed to be the antiderivative or an antiderivative of the given function. So now let's take a look at some examples on how to use this part of the theorem. You'll see it's actually pretty straightforward as long as your upper limit just happens to be a single variable. We're going to make this more difficult in the next few videos where the upper limit is not just a variable, it might be like a function of x, but we'll take a look at that later. For now, we just want to get used to this statement of the theorem above. So take a look at this. We're taking a look at this following signed area function, which is the integral from negative pi to x of cosine t dt. And we want to differentiate this. So what did the fundamental theorem of calculus teach us? Well, it's sort of like these things cancel out, and you just get back the integrand evaluated at the upper limit. And that's what the result is going to be. Okay, notice that the lower limit does not matter at all. It doesn't matter if it's negative pi or negative 300. Here's another example. The integral from negative 3 to x of this function f of t dt. And so this is our signed area function, and we're trying to differentiate this signed area function. And so the fundamental theorem of calculus teaches us that when you differentiate a signed area function, you just get back the original integrand evaluated at the upper limit. And so that's what this would be. And here's something pretty cool. For this example, technically you could use the fundamental theorem of calculus part 2 and evaluate this yourself to find a closed form solution. In fact, this exercise we actually did above with the motivating example. We computed the signed area function, we found the closed form solution, and then we differentiated. And that's how we saw that we just got back to the original integrand. However, for this other example, you can pause the video and try to integrate this term by term, but you're going to get stuck because these functions are a lot more complicated to integrate. In fact, it's actually impossible to find the antiderivative of this one using just simple elementary functions. And so the fundamental theorem of calculus is very, very helpful here because we don't have to do anything complicated. We don't actually have to go out and find any antiderivatives. It just tells us that these things will cancel out, and you just get back the integrand evaluated at the upper limit. Super simple, super straightforward. And let's take a look at one more example over here. In this case, we're trying to differentiate the following signed area function, which is the signed area from 4 to x of this. And so again, applying the fundamental theorem of calculus, the derivative will sort of cancel with the integral, and you'll just get back the integrand, the original function that you began with, evaluated at the upper limit. And so that would just be your answer. Simple as that. And lastly, I want to also dive a little bit deeper on this idea of the inverse operations of the derivative and the integral. So I've already sort of hinted at this, where sort of the derivative and the integral sort of cancel out. They're like inverse operations. And let's see that a little bit more clearly over here. So if we start with a function, f of x, and we build the signed area function by integrating, right? So we integrate from some fixed point to x, f of t dt. Then if we were to differentiate using the fundamental theorem of calculus part 1, which is what we learned in this video, if we differentiate this, these sort of cancel out, and you just get back the integrand evaluated at the upper limit, f of x. So in this case, you can see you start with f of x, you integrate, you differentiate, they sort of cancel out completely, and you just get back where you started. So you recover f fully. Now let's try it the other way. Let's say you start with a function, but you differentiate first to get f prime. Now let's go ahead and integrate. So we get this signed area function from a to x of the integrand in this case is f prime t dt. And then how do we evaluate a definite integral? How do we evaluate a definite integral? Well, we can use the fundamental theorem of calculus part 2, which says that you need to find an antiderivative of the integrand. Well, what is the antiderivative of f prime? Well, it would be, of course, the original function, right? The original function differentiates into f prime. And so just use f evaluated at the upper limit minus f evaluated at the lower limit. So in this case, we started with f of x, and we almost got it back. We got f of x plus some constant. So in this case, we're able to recover f up to a constant. So it doesn't fully cancel out. In this case, the derivative and the integral don't fully cancel out because you don't get exactly what you started with. You actually get a function up to a constant. The main idea I wanted to show over here is that the derivative and the integral, they are two very different concepts, right? In differential calculus, you learn about how this models rates of change, slopes of tangent lines. And then in integral calculus, you learn about the integral, which is like signed areas and antiderivatives. And the beautiful thing is that these two very unrelated concepts get tied together, linked together by the fundamental theorem of calculus. The fundamental theorem of calculus asserts that these are sort of like inverse operations. They undo each other. And so there we go. That is the beautiful and powerful fundamental theorem of calculus. It branches together the two main branches of calculus, differential and integral calculus, and it shows that there's actually a connection between the derivative and the integral operation. They're sort of like inverses, they undo each other. And so that brings us to the end of today's video, in which we finished our discussion of the fundamental theorem of calculus. So we have talked about both parts of the fundamental theorem of calculus, part 2 in the previous video, part 1 in this video. And so in the next video, we're going to sort of build on the fundamental theorem of calculus part 1, which is the signed area version. And we're going to learn how to differentiate signed area functions whose upper limit is not just a variable x, but maybe there happens to be some kind of function in there. So maybe like it's sine of x or x squared. Then how do you differentiate such functions? And even worse, what happens if your lower bound is not fixed? What happens if this also happens to be a variable x squared or some other function of x? And so if you're excited about that, we will take a look and learn about how to differentiate those types of integral or signed area functions in the next video. And so I hope to see you then. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.